Hi, my name is Greg Cott, and I'm an avid flyer. And as you can tell from my bench, I dabble in electronics as well. Um, some of my projects of late have been devoted to flying, and I thought I would show you some of those today, one in particular. I'm currently working on a capacitive fuel gauge system. I actually had one completed that I used last year on the airplane. I fly a Kolb Firefly Ultralight. Of course, this project could be used in any kind of a fuel tank setup. This is the one last year. This is an analog version of it. Typically, what manufacturers do of capacitive fuel probes, or at least they used to, I don't know, it may be digital now, but what they would use is a capacitive type fuel sender, connect that to a oscillator. Here I'm using a 555 timer along with an LM3914 display driver. Those are like the bargraph drivers. They've been around for eons. Also, I've got some NOR gates in here that I use as a frequency to voltage converter. This setup actually worked fairly well. I found out that my calibrations for the range were a bit touchy. Recently I've gotten into the Arduino microcontroller stuff, and I'm trying to design a capacitive fuel gauge using a microcontroller chip, hoping to get a little more accuracy and get the adjustments for calibration not quite as sensitive, so I'd have a range that could be used for any kind of capacitive sender, actually. Let me show you the sender here that it's actually homemade. If you go out and buy a commercial setup for an airplane, get on Aircraft Spruce or something, they can vary and range from $60 or $70 all the way up to probably a couple $100. What I've done here is I've made a homemade one. The outside tube is actually a lavatory supply tube. It's just thin wall copper, and you can go to any hardware or big box store and buy that. It's like $3. The inner tube is a brass tube, and then I've used some nylon material to create some bushings so that the tubes don't touch each other inside. You have to be able to let fuel come up inside the tube, and a couple different ways to do that. What I did on this particular tube, this is an old one, I actually scrunched the bottom of the tube just ever so slightly to get it a bit oblong, and that lets the fuel slip up around one end of the bushing. Another way to do that would be to drill a very small, tiny little hole in the bottom of the tube on the side there, and then make sure at the top of the tube that air can escape. I've just got a plastic boot on there. Don't pay any attention to the cardboard. I'm going to use that for the demonstration for something just to hold on to. At any rate, what I've done here is I've tried to create a demonstration. There's the fuel tank that's out of my plane right now. The tube actually fits down inside that bushing right inside the tank there, and then you can see that the tube is just off the bottom of the tank. Let me get this set up in a second. Here's the display that I used to use in the plane. It's a bar graph. It's kind of small, and that's the other part of this project is that it worked fine, but in bright sunlight it was difficult to see. And I found on eBay a larger display, and this display is also much brighter. I can run this clear. They said the maximum current per segment on this was about 100 milliamps. On the old bar graph, this is typically, like a regular diode, about 20 milliamps is about all you can feed to each segment. So this particular thing, I've got a circuit that I've made over here as well with one of those ready to go to show you. But so far, I'm pretty pleased with the brightness of the display, and hopefully next year when I go flying, that'll show up a lot better. I've got the sketch loaded up on the computer that I used. What prompted the beginning of this project was I found a sketch on the internet on how to check a capacitor. And this particular guy that wrote this, I looked all over the place for his name and I couldn't find it. I'd like to give him credit for writing the original part of this sketch. But typically, as I mentioned before, when you try to find the value of a capacitor, typically you have to change an oscillator or something like that and figure the capacitor that way. A lot of people use the RC time constant properties, and they'll put a capacitor and resistor in a circuit and then use the Arduino to measure the time constant features, and then have the Arduino calculate the math for you, and then get a result that way. This particular guy wrote this sketch in such a way that you don't need any circuitry whatsoever. You just plug your capacitor right into A0 and A2 on the Arduino board, and with his part of the sketch, it just automatically spits out the value of that capacitor. What I got looking at that, and I thought, that might be an easy way to try to look at a capacitive fuel probe in a gas tank. Like I said, the accepted method that you see out there quite a bit is they actually use that fuel probe to help determine the frequency of an oscillator. Then you have to, as the fuel rises up and down in the probe, the frequency changes, and then you have to convert the frequency to voltage, and then you take that voltage and you have to run it through a bar graph driver or your gas gauge, however you want. And what I thought is, why couldn't I try to use this guy's simple sketch just to get the value of a capacitor and just look at the probe directly and just read the capacitance of the probe without any of the rigmarole in the middle. And so that what I've done was I've added to this sketch, and I'm not a programmer by any means whatsoever. I'm just kind of playing with this Arduino stuff. And what I did was I found in there examples that came right with the Arduino ISP software. They have a lot of examples in there. I took the bar graph example right out of their examples and kind of cut and pasted it in. And also I took an averaging or a smoothing example and put that in this sketch as well. Of course, no matter what vehicle you're driving, flying, whatever, fuel is going to slosh around a bit, and you don't want to have your circuit so sensitive that it measures every little change just automatically. So I thought maybe an averaging or a smoothing routine would help dampen that and give me just enough of a delay. So in this sketch, I have it taking 10 samples and then averaging those out, and hopefully when I actually put this into use out in the field, it works the way it seems to on the bench. So let's try to get something rolling here. I'm wearing the camera actually on my headset right now. It may not be centered, but let's get this hooked up here. What's another nice thing about this sketch And if anybody wants to try to build this thing, it will be quite helpful. That right built into this sketch towards the bottom here, there's some serial print statements that look at the capacitance value of the probe, and then it also where the high and low calibration settings are. And the thing that I did with this sketch that it's going to make life simpler if it works the way I intend it to, a lot simpler, is that I can map the high and low readings to any ranges that I want. So let's say you're going to build one of these on your own. Like I said, you can go to the store and build this probe for $5. But between the brass tube inside and the tube on the outside. When you get done building it, your value of capacitance might be a bit different than mine. Or right now, since I've got this breadboarded, of course I've got all these wires hanging out and there's stray capacitance flying all over the place. So it's not going to be the same as when I actually get it mounted in the plane. So I may have to tweak it a little bit. But right here in the sketch, right in these map statements that I have right here, I can change these numbers at will and get it in the plane and just give me a range of numbers that I can set the high and low ranges to. And then this tank, actually, you can see the fuel through my tank. So when I actually get this put back in the plane, I can do it at full, I can do it at empty, I can do it at half level, and make sure that my display is telling me or giving me correct data there. So anyway, let's see if we can get this fired up. What I've got here is a PVC tube, and I've actually got the actual fuel that I use in the airplane. I have a two-stroke engine, oil and gas mix, and I've actually used the actual fuel and put it inside this PVC tube here. Actually, this probe, you know, it would probably work even in water. You would have your probe, water would be a different dielectric for the probe, and you would end up with a different set of numbers, but I don't see why this program wouldn't work for just about any fluid at all. And the length of the probe could be whatever you want. That's the beauty of this program, is you just plug in whatever range of numbers that you're dealing with once you decide what the probe gives you at empty and full, no matter what the fluid is. And then just map the numbers, and I don't see why it wouldn't work in any kind of fuel whatsoever, or fluid. So let's kick in the serial monitor here a second and see what we get. Yeah, right now my probe is out, just laying on the bench. It's showing me the capacitance value is 47, dry. Calibration low right now is set about 45, and my calibration high is set about 81. So that suggests that my range from low to high is from 45 to 81, which isn't very much. And this is in the picofarad range as well, which is very small. But the Arduino being digital, I can take that range of numbers and divide it up into little bits between 0 and 1023, chop it up into that many bytes or bits, and get that much accuracy out of it. So let's pick this up and actually put it inside the fuel here and see if we can get a result on my display over here. And there it goes. Oops, I'm getting an intermittent here. Oh, these are short. No wonder my wires are shorting out here. Okay. That's better. Okay, now let's try this again. Probe is out of the fuel, and as I drop it in, there's a delay there because it's got to take 10 samples, and as I drop it in, you can see the lights are lighting up. I'm dropping in very slowly, and you, oh shoot, my wires came loose again, doggone it. Let's see if I can get a better connection here. It's a bit Mickey Mouse way of showing you, but and in practice, you'd want to keep the wire between the circuit and the probe as short as possible to eliminate any stray capacitance. But you can see that, okay, probe is out. Slowly drop it in. And you can see the lights coming up. Probe's about halfway in, and I've got half my lights lit, so it appears to be working. Slowly dropping the probe. And as the probe goes in full, the lights come up full. I have a couple pots in here on the breadboard that I can adjust the high and low range with. And now as the probe is all the way in, you can see my maximum capacitance right now is saying 87. My calibration low is 45. My calibration high is about 81. So I could tweak the calibration high a little bit just to get it right. But like I say, if you put enough range on those pots, once you actually mount this thing, you just whether it be in a motorcycle or whatever, as long as you can see the fuel or you know how much fuel you've got in there, you just use those pots to set your high and low range, and everything else should take care of itself. And so far on the breadboard, it seems to be working just fine the way I intended. Hopefully next year I'll have a little more accurate fuel gauge, although my analog version here wasn't all that bad at all. Matter of fact, it's cheap to make, and it worked well enough where if this digital one didn't work the way I wanted, I would just put this right back in there again, and because it worked quite well. You know, now that winter's here, you want something to play with. Here's you can see the size of the display, the old display. Here's the new one, right there, quite a bit better, bigger. Over here, I've got the new one. I've already built the circuit. I was confident enough in this where I went ahead and built this. The difference in circuit, here's the analog version, here's the digital version. The digital version, since this display, I can run it a lot harder. I'm running it about a half amp or so. And a half amp is enough current where you start creating some heat. All the, or most of the parts that you actually see on this board are in support of running this display at a higher current. The chip uses nothing at all. So I've got a transistor regulator in here that I've put in here just to make sure that I'm feeding a nice steady current to the display so it doesn't flicker on me or anything. But let's fire it up. And I'm using a variable capacitor that I pulled out of an old radio chassis as my simulated fuel gauge. But you can see the brightness of that display is considerable. And as I change the capacitor, you can see the lights changing. This is that same exact sketch. Same pots right here, a low adjust, a high adjust. So I can adjust the range to whatever you're using. And one feature I added to the sketch is when you get, I mean, red light's bad enough, your fuel's getting pretty low at that point, but you still have some. And then if you get to the point where you're just about out of gas altogether, I've got it so that it actually flashes at you just to try to catch your eye even more. Of course, as I fly the airplane, most pilots fly more on time than they do looking at a fuel gauge, because aircraft fuel gauges have a tendency to be incorrect a lot of the time. So you know about what your engine burns in fuel at a given rate, gallons per hour. So most pilots just fly, I can fly an hour and before I have to land for fuel, or 2 hours, or whatever your airplane you're flying. But I'm on the ultralight, I've actually got the LED bar graph fuel gauge that I use, and then on the tank here I also have a float switch installed, which gives me a warning light at 1 gallon left. I've got 3 different ways of telling me how much fuel I have, so if I were to ever have a problem with running out of fuel, it's definitely my fault, not the airplane's fault, because I've got three different ways of checking for that. You just can't be too safe, just the safer the better. So anyway, yeah, that'll be next spring's project, is getting that mounted in there. Now that this is the first time I've tested with actual fuel today. And I'm pleased with the results, so I'm going to go ahead and finish building the circuit the rest of the way. Here's an actual, here's the box that we'll use to put it in. And here's the pots to adjust the high and low ranges with, and I'll get that labeled up again. A couple of the other things that I've done. This is one of the first things that I built for the plane. This is actually a vertical deviation meter, and it works off of pressure. There's a pressure sensor inside here that gives me barometric pressure, and then the way this works is that it just shows me a change in altitude. It doesn't actually act like an altimeter. It just tells me if there's been a change in altitude, either up or down. And I find that flying the ultralight, it's such a light airplane that even a thermal, the same thermals the Hawks ride around on, can be changing my altitude, and I don't necessarily know it right off the bat. The altimeter that I have in the plane is not that sensitive, so this gives me an indication right off the bat if my altitude is changing up or down immediately. This is my own invention, actually. This kind of works off an analog principles as well, but I'm pretty pleased with the result on this as well, so that's going back in the plane next year. This is a homemade intercom box. When I go flying, I can plug the radio into this, and then I have a speaker in my one of my headphone cups, so that as I fly, I can narrate a flight, or you can hear air traffic control at the same time that I'm flying. You can hear what I hear, and being inside the earphone cup, it gets rid of a lot of the engine noise, so that the audio is actually pretty good. And this is a homemade gizmo as well. So I've just about run out of space on the airplane to put gizmos, so I'm going to have to think of something else to do. But in the meantime, I thought I would show you this project, because not only airplane guys, but anybody that likes electronics, or likes to play with, like I said, it could run in a motorcycle or just about anything. You could make this fuel gauge. I don't see why you couldn't do it in a car as well. So the amount of money I have in this project, let's see, the display was $5. Probe was $5. the individual parts, the transistors I have actually pulled off of old chassis. If you had to buy these transistors, these are actually smaller transistors that can handle 100 milliamps or less. I would say that the total cost, the Radio Shack board was, I don't know, $2.50. So you could build a nice, decent fuel gauge for anything that you're using for 20 bucks, 30 bucks maybe at the outside. Compare that to 150 bucks. I'd say it's well worth the effort to go ahead and try this. You can always, if you like the video, you can always just drop me a comment in the video section there, and I'll try to answer your comments and send you a copy of the sketch. This Arduino stuff is not licensed, or it's licensed under a general license where everybody can use it, kind of thing. Anybody that writes anything that's they don't want you using, they usually tell you that in the software. And this particular sketch had nothing in it at all that said don't use it. So I went ahead and used the guy's part of the sketch and then modified it in addition to make it do what I needed it to do. So anyway, there it is. Hope you enjoyed the vid, and have fun with your projects.